Okay, so get ready because we are diving deep into some serious AI today. We're talking neural Turing machines, NTMs. You sent these excerpts over, and wow, this research paper is like the talk of the town.
Yeah, and what's so groundbreaking about it is it's not just, oh, look, another AI. It's really looking at how machines learn and think in a whole new way.
Yeah.
Like, how can we get machines to actually understand information the way we do?
Right, it's like we're trying to figure out the secrets of our own brains and then bottle it up and give it to a machine. And if these research excerpts are anything to go by, it seems like we're getting closer.
Yeah, definitely. And, one of the things they talk about is moving beyond the limits of those old neural networks.
Hmm.
The kind that could process information, but ask it to, like, plan a vacation or write you a poem. And
It would just crash and burn.
yeah, they just didn't have the memory for it or the reasoning skills.
Right, like trying to write a whole novel on a sticky note. You're going to run out of space pretty quickly. And that's where this whole working memory thing comes in, right? The paper mentions it a lot. So for those of us who haven't had their coffee yet, what exactly is working memory?
So think of working memory like that mental whiteboard that your brain uses. It's where you hold on to information, you can manipulate it, you can make sense of it. Like right now, you're listening to me, you understand hopefully what I'm saying, but you're also remembering what you did this morning. That's your working memory in action. And that's what NTMs are trying to recreate by giving machines a separate memory bank to work with.
So regular neural networks, they're stuck trying to juggle everything in their heads, while NTMs, they've got a whole whiteboard to scribble notes and connect ideas.
Right.
That seems like a pretty big advantage.
Huge, huge advantage.
Okay.
Because it changes what they can do, right? Those more complex tasks, the human-like tasks. It changes what they're capable of.
Okay, I am on board. Now let's break this down a little bit. The paper uses these terms, controller, memory bank, read and write heads. It's a lot to take in. So what are these components and how do they all fit together?
Okay, so imagine a library.
Right.
And then the memory bank is like this huge library, bookshelves, tons of books. Each one is a piece of data. Our controller is like this really efficient librarian. Knows where everything is. The controller is the one making decisions.
I like this analogy. Okay, so the controller calls the shots. The memory bank is the information hub. But how do they actually interact? That's where these read and write heads come in.
Exactly. That's our librarian's tools. So the read head allows the controller to go and find specific information in the memory. And the write head, as you might imagine, lets it add new information or update what's already there.
Okay, so we've got this super organized system for storing, finding, and using information. Kind of like how our brains are supposed to work, right? But hopefully the NTM is a little more organized than my brain on a Monday morning.
Well, that's the thing. One of the things that makes them so amazing is that this whole system, this controller, the memory, everything, it's all differentiable.
Differentiable. Okay, that sounds like we're about to do some calculus here. What does that actually mean in, like, normal terms?
Basically, it means that NTMs are capable of learning from their mistakes, right? Just like we do. And that differentiable quality lets us use these really cool mathematical tools to train them. So they're not just stuck with whatever we program them with.
So instead of programming every single step, we're saying, here's a bunch of examples, figure it out.
Right, figure it out.
That's amazing.
It's like teaching a kid how to ride a bike. You can explain it to them, but they learn by trying and falling off and trying again. NTMs can do the same thing with information.
My mind is already blown, and we're just getting started. Now, the paper also mentions these addressing mechanisms, content-based and location-based. It sounds like there's different ways for our librarian to find the right book on those shelves.
Exactly.
So how do these addressing mechanisms work?
Okay, so imagine you're looking for a book in a real library. You could be looking for a specific title. That's kind of like content-based addressing, right?
Right.
You're searching based on what you know about the information itself.
Makes sense.
But what if you only remember where you saw the book, not the actual title? Like it was on the bottom shelf, way in the back, covered in dust.
Oh, yeah, that sounds like my kind of reading material.
That would be location-based addressing. Like using the Dewey Decimal System or remembering a specific shelf number. And NTMs can actually use both of these methods, which makes them very, very flexible and very efficient in how they access information.
So they can find information based on what it is and where it is. That's kind of like having a mental map of the entire memory bank.
Yeah.
Okay, I have to see this thing in action. The paper mentions these experiments where they really put NTMs through their paces.
Yeah, the experiments are really cool.
So first up, the copying task. Sounds kind of basic, right? I mean, we do it all the time. But for a machine, that's actually a pretty big deal, memory-wise.
Yeah, think about it. Like if you had to copy down a list of words, but you could only find your notes by remembering what each word meant, not where it was on the page.
That sounds more like a nightmare than a memory task.
Well, that's why this CompuTask is such a good test for these NTMs, right? So they fed the NTM all these random sequences, just binary vectors, and they tested if it could spit them right back out.
And I'm guessing it did way better than those old LSTM.
Oh, yeah. NTM wasn't just copying. It was like the ultimate copycat. And get this, they trained it on sequences like 20 elements long, but then it could copy sequences of 100 elements or more. No problem. Zero errors.
Wait, so it's like it learned how to copy anything no matter how long. We're talking about going from like learning the alphabet to writing a novel, basically.
That's the thing about NTMs. They're not just memorizing a pattern. It's like they're learning the algorithm, the actual how behind the task.
Okay, so what's going on inside the NTM's brain when it's doing this? Did the researchers like peek inside its memory bank?
You did, and it was really cool. It's like the NTM had created this little program for itself. Move to the start, read the input, write it down, move to the next spot, repeat. Very elegant, very efficient.
So it's like the NTM became this tiny little programmer figuring out the smartest way to get the job done.
Right.
And it's using both, what was it, content and location-based addressing to make it happen.
Exactly.
Okay, that's impressive.
And, you know, it shows a really cool thing about these NTMs versus like a regular computer. With an NTM, you're not stuck with this like rigid memory access, you know. It can jump around, it can make these connections just like our brains do.
Right, right. Okay, copying, that's cool. But let's see this thing really shred its stuff. What about this repeat copy task?
Oh, yeah. So imagine you have to copy that list, but then you have to repeat it a certain number of times.
Okay.
It's like a for loop in programming. It's like next level copying.
Okay, so we're talking about nested tasks now, things inside of things. That's definitely getting more complex. So how did our NTM handle it?
Pretty darn well, actually. At least to a point. It could handle way longer sequences and more repetitions than it was trained on, which again speaks to that ability to generalize. But there was a bit of a catch.
There's always a catch, isn't there? What was it? Did the NTM finally hit a wall?
Well, it wasn't a total failure, but it did start to struggle with keeping track of all those repetitions when the numbers got really large, like beyond what it had seen during training.
So it's like the NTM was acing the algorithm part, but maybe it missed a few days of like arithmetic class.
That's a great way to put it. And you know, that little hiccup actually tells us something interesting about how these NTMs represent information. It suggests that maybe directly representing numbers, like literally storing the number itself, might not be their strong suit.
Interesting. So they have their own way of thinking about numbers. Okay, enough about numbers. Let's talk about this associative recall task. Now that one really sounds like how our brains work, right? Making connections between different things.
Yeah, exactly. Like think about how you remember stuff. Maybe a song reminds you of a certain memory, or a certain person always makes you think of a place. This experiment was all about testing if NTMs could make those kinds of connections too.
So it's not just remembering things in order, it's about understanding the relationships between them.
Exactly. So they showed the NTM a bunch of items, and then they were like, okay, what comes after this one? Like giving it a jumbled to-do list and seeing if it can figure out the order based on the context.
Okay, that's seriously cool. So how'd it do? Did the NTM become the ultimate taskmaster?
Well, the NTM variations, both of them with their fancy controllers, they smoked the standard LSTM on this task. It seems like having that external memory bank, it's like having a well-organized filing cabinet for your brain.
Right.
It lets the NTM create this web of associations, making those connections way faster and way more efficiently.
So it's like the NTM was building its own little mental map of the information, you know, like drawing lines between the ideas, just like we do when we're trying to remember something.
That's a great way to put it.
That's so cool.
And, you know, it's something that traditional neural networks, they really struggle with. That ability to make those leaps, to access information associatively, it's a game changer for all sorts of tasks that require context.
Okay, awesome. 2 down, 2 to go. What about this dynamic n-grams task? That one sounds a little, I don't know, intimidating.
Well, this one gets into the world of probability, prediction. Think about trying to guess the next word in a sentence.
Okay.
You'd use your knowledge of language, right, and the patterns you've observed to make a guess.
Right. Like if I say peanut butter and, you're probably going to say jelly.
Exactly. That's what n-grams are all about. They capture those probabilities based on sequences of things. So this dynamic n-grams task, it was all about testing whether these NTMs could learn these probabilities on the fly, and could they adapt if things changed.
So it's like testing if the NTM can become this master of predicting what comes next, even if the rules are constantly changing.
Exactly. And you know what? The NTM, it consistently did better than that standard LSTM. It's like it was building this statistical model in its memory and constantly refining it based on the information it encountered.
So it's not just storing the information, it's analyzing it, finding patterns, making predictions about the future.
Yeah, that's right.
That's amazing.
It's like giving it a puzzle. Yeah. Watching it not only solve the puzzle, but get faster every time it sees that puzzle again.
Okay, that leaves us with the final experiment, priority sort. And sorting, that just sounds so simple, but I have a feeling there's more to it than meets the eye.
Oh, yeah. Sorting might sound straightforward, but actually takes a good amount of, algorithmic sophistication to do it really well. It's a key operation in computer science.
So for this experiment, were they asking the NTM to, organize its digital sock drawer or something?
Not quite. They gave it these sequences of data, right?
Mm-hmm.
And each one had a priority value. And the challenge was to rearrange everything in the right order.
Ah, so it's not just about alphabetizing. It's about understanding what's more important, like ranking information. Okay, so how did our NTM handle that?
It did pretty well. And this is where it gets interesting. The NTM, specifically the one with that feed-forward controller, it ended up needing 8, count them, 8 read and write heads to really nail this task.
8? That's a lot of brain power. What does that tell us?
Well, it kind of suggests that these feed-forward controllers, while they are powerful, they might need a little extra help compared to those recurrent ones when things get really complex. It's like trying to juggle 8 balls at once. You need a lot of coordination.
Right. It makes sense. But even with all that juggling, the NTM still managed to outperform those LSTMs.
Oh, yeah. It showed that it could learn and actually execute complex algorithms. It was exceeding the capabilities of those more traditional networks.
Okay, well, I have to say, I am thoroughly impressed. This NTM really is like the overachiever of the AI world. We've seen it copy, sort, predict. It's like the Swiss Army knife of AI. But we've gone through all these amazing experiments, and I still have one big question. What does it all mean? I mean, we've seen this NTM do some pretty amazing things. Copy, sort, predict. It's like the overachiever of algorithms. But why should we care? What's the bigger picture here?
Well, that's the million-dollar question, right? And the answer, it's exciting. It's a little mind-boggling. We're not just talking about mimicking human thought here. NPMs, they're hinting at a future where machines can learn and solve problems in ways that, frankly, we haven't even thought of yet. Remember that copy task? How it could handle those super long sequences it had never even seen before? That's a big deal. It means it wasn't just memorizing. It was learning the concept of copying.
So it's like showing a child like a couple of addition problems, and suddenly they understand how to add any numbers, not just the ones you showed them.
Exactly. It changes everything about how we think about developing AI. Imagine being able to teach a machine a complex task just by showing it examples.
Instead of spending years writing code to teach a self-driving car how to navigate a roundabout, we could just show it a bunch of dash cam footage and it would figure it out.
That's the idea.
Yeah.
That ability to learn algorithms, not just data, it's huge. It's like we're giving machines the tools to learn how to learn.
Okay, that's mind-blowing. And what about those memory capabilities, that associative recall task that really stood out to me? How NTMs can connect information, it feels very human.
It does. And think about all the things our brains do without even thinking. Things that still really trip up AI. Understanding language, planning, creativity. These are all things that depend heavily on memory. Not just storing information, but understanding the relationships, making connections.
Right. It's like the difference between memorizing a phone book and actually understanding how to communicate with another person.
Exactly. And traditional neural networks, they kind of hit a wall there. They don't have that same flexible memory, that processing power that these NTMs have.
So it's not even just about bigger data sets or faster processors anymore. It's about changing how machines think about information in the first place, how they interact with it.
Yeah, you got it.
This has been incredible. We started with the nuts and bolts of NTMs, and now, the potential here is just
Pretty amazing.
And for everyone listening, remember, this is just the beginning. AI, it's always changing, always evolving. NTMs, they're just one piece of the puzzle, but they're a really exciting piece. They suggest that we might be on the verge of something truly groundbreaking, creating machines that don't just process information, but that actually think more like us, and who knows what incredible breakthroughs are waiting for us just around the corner. So keep those minds curious, and we'll catch you on the next deep dive.